All right, let's go ahead and get started. This is going to be your homework help video for the fundamental theorem of algebra homework. Start with problem number 1 here. State the number of complex zeros for each function. So this really asks you to apply our fundamental theorem of algebra and also understand our number types. Complex, that includes everything. That includes real numbers, rational, irrational, and imaginary. And the fundamental theorem of algebra states that there are this number of roots. Another word for roots is zeros, and all of those zeros are going to be complex. So it's just as easy as that. There are 3 complex zeros for this function here, 5 for this one over here. We don't have to worry about anything else going on there, just the degree of the function indicated by its highest exponent. State the possible number of imaginary zeros for each function. So for this, we have to combine our understanding of fundamental theorem of algebra and conjugate root theorem, which states that imaginary zeros must come in pairs. Sometimes we call this the buy one, get one free theorem. So if there's 3 total here, well, I can always have 0. I can't have 1, but I could have 2 imaginary zeros, but I can't go up to 4 because then I would exceed the 3 total. And number 4 is the exact same, 0 or 2. Now, real zeros, for this, it can be a little bit easier to do if you start pairing them up, real and imaginary. Because real zeros, it seems like there shouldn't be any restriction on that. But because the only other option is imaginary zeros, we need to make sure we're leaving an even number of roots to be imaginary. So this one's going to have 4 roots. The possible combinations could be 0 real, I'll just say 0R, and 4 imaginary. We can't do 1 real, though, because that would only leave 3 spots, and then we would have an unpaired imaginary. So we got to go up to 2 real and 2 imaginary. Then the last combination would be 4 real and 0 imaginary. So the possibilities were 0, 2, or 4. For this one here, there's a total of 3. So that gives us the options of, it's got to add up to 3. I could do 1 real, 2 imaginary, or I could do 3 real, 0 imaginary. Notice my imaginaries are even, but my options for real are actually odd here. So it's sort of like a quick way to know if you're doing this right. Imaginary zeros will always be just a list of even numbers up to the highest degree. Real zeros will be even or odd up to the highest degree. And if it's an odd degree, it will be all the odd numbers up to that. If it's even, it's all the even numbers up to that. All right, rational zeros. Again, we have to understand our number types here. Rational, what's a rational number? It's a number that can be expressed as a fraction. And we learned that rational zeros are always of the form p over q, but I often just say last over first, where p are the integer factors of our last term. Here it's just 1 and 2. Well, it's plus or minus 1 or 2, but we'll address that in a second. And q are the integer factors of the leading coefficient, 1, 3, and 9, all divide into 9 evenly. Now let's make all the fractions possible with elements from p divided by elements from q, and we'll get 1 over 1, 1 over 3, 1 over 9, so that's the first element of p divided by every single one of these. Then I'll move on over to the 2 and do 2 over 1, 2 over 3, and 2 over 9. This can be simplified down a little bit. And also let's add that plus minus in front now, because when we said integer factors, that includes the negatives. So now I've got 1, 1/3, 1/9, 2, 2/3, and 2/9. Look to see if there's any repeated fractions, simplify all your fractions. Now you can put them in order of least to greatest, but I think if you can get this list, you'll be able to pick the correct answer. All right, find all zeros. I did problem very similar to number 10 in class. So let's do number 9. What I'm going to first try is factor my grouping. If I ever have 4 terms, I try this. And that looks like it's going to work. I mean, these look pretty darn similar, these two groups. I'm going to take an x squared out of the first, leaving behind an x minus 13. Let me take a -1 out of the second, leaving behind an x minus 13. Looks like we can do factor by grouping, so now I regroup. X squared minus 1, x minus 13, zero product property. This is just going to give me x equals 13 as one of my zeros. This right here, I'm actually going to show the work for. Adding 1 to both sides, taking the square root, x equals plus or minus 1. And what's useful by the fundamental theorem of algebra is we know that we're done here. I count 1, 2, 3 zeros. This is a third degree polynomial. I know I've got all of the roots. This one over here is a little tricky because once you find the first one, x equals -5 works pretty well. -5 cubed is -125. It's difficult to find the next ones. You have to actually end up doing synthetic division to simplify this down with your known root of -5. So 1, -5, -5, 25, 25, -125, 0. And then take this and do the quadratic formula on it to get your 2 remaining zeros. Let's take a look at some of these on the back side. 11, this is an example of what we call quadratic form. It's simple factoring, but instead of setting it up your structure with just an x here, you do an x squared. And I'll show you why this works by actually foiling this out. Let's see. 2 numbers that multiply to be -7, but add to be -6. I think that'd be -6 and +1. No, -6 and... Why am I having such a hard time? No, -7 and +1. Yeah, multiply to -7, add to be -6. I'm going to FOIL this just to double check that it works. So first, inside, outside, last. We get an x cubed when we do our first. Inside, -7x squared. Outside, plus x squared. Last gives us a -7. Combine like terms, and you'll see that this goes back to that original expression. So if you ever get a trinomial, look to see if it's got these exact exponents, 4, 2, and then nothing. And you'll know that you can do simple factoring, but you just got to set up your structure with an x squared in that first position. I believe the instructions here wants us to solve it all the way. Yeah, find all zeros. So I would need to now set these equal to 0 and solve. And I hope we're okay if I just kind of shortcut this to plus or minus the square root of 7 and plus or minus I. And there's all 4 roots. All right, I'll pick another one. 14. Here 14, don't miss out opportunities to pull out a greatest common factor like in 14. I can write an x squared down in front here, leave behind an x squared plus 6x plus 5. And now this gives me, I'm actually going to split it into an x and an x. And then this here, I'm going to add the parentheses back in, can be factored into 2 numbers multiplied to be 5, but add to be 6, 5 and 1. And now this gives me a 0 at 0. This gives me another 0 at 0. So I'm going to say 0 mult 2. This gives me a 0 at -5, and this gives me a 0 at -1. So there's all of our answers. We got all 4 of them, as predicted by the fundamental theorem of algebra. All right, I did 15 in class. Let me pick another one. 17. I'll do 17 and 18. So we got to write a polynomial And it says least degree with integral coefficients, but in parentheses I tell you that's standard form with no fractions. And don't forget the conjugate root theorem. So I'll just help you with all of these. That means that I need to include the conjugate because we can't just have a root at like negative I. We have to also get a root at positive I, or else we won't have integer coefficients. The only way to avoid imaginary coefficients is to include the conjugate root. This one doesn't have any irrational or imaginary, so we can kind of ignore that. And let me now use factor theorem to state that if I have a 0 at 4/3, then x minus 4/3 must be a factor, also x minus 3/2. Now, if I want to avoid fractions, I've got to multiply these by the denominator of the fraction, which you can do a little experiment here and actually still solve for the root. You'll see the root hasn't changed location, but as I simplify these, you'll see no more fractions, which is nice. All right, and now we just need to do some semi-extensive foiling and distributing. Let's see, 9x squared minus 12x minus 12x plus 16. Got to multiply that to a 2x minus 3. Combine my like terms. Multiply that to a 2x minus 3. Now when I do this next distribution, I just make sure I get every combination possible by just going first to first, first to second, and then I'll do second to first, second to second, third to first, third to second, and it will work out, let's see, 18x cubed minus 27x squared minus 48x squared plus 72x, my last, plus 32x minus 48. Combine like terms, and I'm going to get the function 18x cubed minus, let's see, that's 75x squared plus 104x minus 48. That's good for that one. This one here, factor theorem. Got x minus 2, x minus 1 minus I, and x minus 1 plus I. You should technically put the parentheses in here like this and then distribute the negative, but you can actually skip this step because then these two factors will just switch spots. And it's going to still be the same because of the commutative property. Now the first two we should multiply are the conjugates because a lot of nice canceling will happen. So I got x minus 2 over here. This leaves x squared minus x plus ix minus x plus 1 minus I minus ix plus I, and then negative I times I is negative I squared. That's going to become a positive 1. Let's see if some canceling happens. The ix and the negative ix, the negative I and the positive I all cancel. See what's left behind, x minus 2 times x squared minus 2x plus 2. One more set of distribution, and then one more set of combining like terms. And we will be done with this problem. Because I was talking, I probably made some mistakes, but we'll see. 4x squared plus 6x minus 4. I don't know, probably made a mistake. Let's see. Looks like it matches. All right, well, that's that for this homework help video. Hopefully you found that helpful, and have a good rest of your day.